All right, this is AP Podcast 8.2, and today we're going to add on to this idea of entropy, and we're going to talk about free energy. So, free energy kind of originated from Josiah Gibbs. He was an early pioneer of free energy, especially in the area of chemistry. So, free energy is abbreviated with this letter G, and it's the maximum amount of energy available to do work from a reaction. So, what can we do to get work done by the energy that's given out from a reaction? It's also used to determine if a reaction will occur spontaneously or not. And we'll talk about what those signs mean in just a second. But calculating Gibbs free energy. Gibbs free energy cannot be calculated directly, or it cannot be measured directly, but it can be calculated from other measured quantities. And this is the general formula right here, G being the free energy, Gibbs free energy. H is enthalpy minus the temperature in Kelvin times the entropy. But this is the really important way and the most common way that we see it is delta G equals delta H minus T delta S. And this is for constant temperature and constant pressure. G is the free energy. It's usually in kilojoules per mole. Enthalpy is usually also in kilojoules per mole. The Kelvin temperature, make sure it's Kelvin, don't use Celsius. And then S is the entropy. And usually when you're looking up entropy on tables, or if they give it to you in a data table, you're going to see that as joules per Kelvin mole. So you just need to watch out that when you go to do all this math, that either all the units are in kilojoules or all the units are in joules. It doesn't matter which way. You just need to make sure that they're matching up so that you can do this math. Really quickly to summarize then, what do each of these things mean in terms of when it's positive or when it's negative? Because this is a really important concept for you guys to have. Especially on the AP test. They ask questions about if delta H is positive, what does that mean? And you have to be able to tell them. So delta H being enthalpy, if it's positive, it means you have an endothermic reaction. So energy is going in. If it's negative, it means it's an exothermic reaction. If delta S is positive, that means it's spontaneous. It's becoming more random. It's becoming more disordered. And then if it's a negative, it's not spontaneous. Or you also hear that it's spontaneous in the opposite direction. Either way works. Delta G, which is the one we introduced today, if delta G is positive, it means it's not spontaneous. It's not releasing energy, which is not a good thing. We want delta G to be negative. We want it to be giving off energy that we can use. That makes it a spontaneous reaction. So if delta G is negative, we have a spontaneous reaction. And this is a really key table for you guys to be able to do and to understand. All right, when delta G equals 0, we have a special case. If delta G equals 0, the system is at equilibrium. So no energy is being given off, no energy is going in. It's just at equilibrium. If we do that to this equation that we have already used before, that delta G equals delta H minus T delta S, if we're at equilibrium and this is 0, we end up with 0 equals delta H minus T delta S. And then we just do a quick rearranging of this and we see that delta H equals T delta S. And this is the equation that you can use when you're at an equilibrium because the Gibbs free energy is not involved in that. So this question says, what is the boiling point of a solution where delta H, or the heat of vaporization, is 23.5 kilojoules per mole and delta S is 34.5 joules per Kelvin mole? Well, the first thing is they're asking us for the boiling point. So they are asking us to calculate T, which is the temperature. And you may be asking yourself, well, I don't have a delta G, so how am I going to use this equation that we just talked about being so important? Well, if you remember, a boiling point is technically at an equilibrium. It's the equilibrium point between a liquid and a solid, or a liquid and a gas. So what we know then is delta G is 0. So we can use that equation that we just talked about, and we can plug in and we can solve for T, because they gave us delta H and they gave us delta S, and we can find out what T is here. The big thing though, this is kilojoules and that is joules, so I need to watch out when I'm doing my math to make sure that they match up. And I'm just going to go ahead and convert everything to joules. So if I make this into joules from kilojoules, I bump the decimal 3 places to the left. So let's see, if I rearrange, T is going to be equal to delta H over delta S. And then if I plug in my numbers, I want to make that joules. So this is 23,500 joules per mole. And then this other one stays the same. It doesn't change. So 34.5 joules per Kelvin mole. And when I divide those, I end up with 681. And we can see that the joules cancel, the moles cancel, and I'm left with Kelvin. So 681 Kelvin must be the boiling point of this solution. All right, also remember that if you have an element in its standard state, delta H is going to be 0. You're not going to have a value for it. And this is also important. You don't have this on your paper, but you should write it on there. It's not on your note outline. Delta G, so the Gibbs free energy for the formation, is also 0 for an element in its standard state. So if we were talking, say, oxygen gas, and you were looking up that information in the back of your book in the appendix, you would see that delta H is 0. You're also going to see that delta G is 0. So those elements in standard states, the only thing you're going to find for them is a delta S in entropy, because the only thing that has a 0 entropy is a crystal at absolute 0. So this guy will have an entropy, but it will not have a delta H or a delta G. Okay, and then I think this is the last thing. It's just another table here where we're incorporating all these signs. And the important thing is that we want to remember this formula that we have right here. So what we're looking for is if delta G is negative, so a negative equals a spontaneous reaction. So we can say that these are for sure going to all be spontaneous, but we're going to put some guidelines on them as to when they are. And this delta G right here is positive, so this is going to be not spontaneous. If we look at this first one, delta G is negative, so it's spontaneous. But if we think of delta H and delta S here, delta S is positive. So if delta S is positive, no matter what the temperature is, I'm going to keep subtracting by this is going to be a positive. So this is going to be a negative minus a positive, which is just going to make it more negative. So this is yes, and this is going to be at all temperatures. So no matter what the Kelvin temperature is, that delta G is always going to come out negative. The next one here is the exact opposite. So this is a positive, not the exact opposite. This is a positive, and then this is also a positive. So I have a positive minus a positive. In order for this to work, though, we need the delta T here, or the T, the temperature, to be relatively high, because we need this subtraction to come out negative in order for delta G to be negative and for it to be spontaneous. So this value right here has to be bigger than the delta H. So this is yes, but it's only yes at higher temperatures. So at high temps. This guy right here is true only then at low temps. And then this one's just no altogether because delta G will always come out positive. So just being able to analyze the signs using this reaction to determine spontaneity or not according to what you see, that's a key thing that you should get out of this podcast. And that is it. So it's a pretty short one, and it's dealing just a lot with what do the signs mean and how can we predict whether it's going to be a spontaneous reaction or not.